Your teacher told you there are three states of matter: solid, liquid, gas. Clean, simple, done. Here's what your teacher didn't tell you. There are four. And the fourth one, the one that got left off the list, makes up more than 99% of all visible matter in the universe. The sun is the fourth state. Every star in every galaxy is the fourth state. The aurora borealis is the fourth state. Lightning is the fourth state. The solar wind streaming past Earth right now at hundreds of kilometers per second is the fourth state. The three states you learned describe a thin, quiet, low-temperature sliver of reality, the conditions on the surfaces of a handful of rocky planets. The universe, almost everywhere else, is doing something completely different. The fourth state is plasma, and once you understand what it actually is, not the name, the physics, you'll never look at a star or a lightning bolt or a neon sign the same way again. Let's fix the most common wrong answer first. Plasma is not just hot gas. I know that's what it sounds like. You hear gas gets really hot, electrons fly off, you call it plasma. And it feels like a temperature story, just another point on the thermometer. But that's wrong. It misses the thing that matters. Here's what actually happens. In an ordinary gas, air for example, atoms are intact. Electrons are bound to their nuclei. The atoms move fast, collide with each other, bounce around. The gas is electrically neutral. The positive charge of the nucleus and the negative charge of the electrons cancel out, atom by atom. Add enough energy, enough heat, or intense radiation, or a strong electromagnetic field, and electrons stop staying bound. They rip free. The atom loses one or more electrons and becomes a positively charged ion. You now have a mixture of free electrons and positive ions moving independently, no longer paired up. That mixture, that's plasma. And the key difference isn't the temperature, it's the charges. In a neutral gas, electromagnetic forces are irrelevant at the bulk level. Everything cancels out. In plasma, you have free charges everywhere. Free electrons moving through the plasma create electromagnetic fields. Those fields propagate across the entire plasma simultaneously. Every other charged particle feels them and responds. Plasma isn't a crowd of fast-moving neutral particles. It's a collective electromagnetic entity. Every part of it coupled to every other part through fields that travel at the speed of light. Calling plasma hot gas is like calling a symphony orchestra a room full of people making sound. Technically adjacent, physically completely wrong about what's happening. Now, the number that should genuinely stop you. More than 99% of all visible matter in the observable universe exists as plasma. Not in labs, not in exotic conditions, naturally, pervasively, overwhelmingly. Every star, our sun, the 100 billion stars in the Milky Way, the 100 billion galaxies, each containing their own hundreds of billions of stars, all plasma. The interstellar medium, the thin material drifting between stars, is largely plasma, ionized by the intense ultraviolet radiation from nearby stars. The intergalactic medium, the diffuse material between galaxies, is plasma. Earth's ionosphere, the upper layer of our own atmosphere, starting at about 60 kilometers altitude, is plasma, ionized by solar UV radiation. The solar wind right now, a continuous stream of charged particles flowing outward from the sun at 400 to 800 kilometers per second, is plasma, washing over Earth's magnetic field, driving the dynamics of our near-space environment. The three states of matter you memorized describe conditions on the cool, solid surfaces of rocky planets, the most atypical environments in the universe. We live in a statistically extraordinary location, and were taught physics calibrated to that location. Almost everywhere else, the interiors of stars, the space between them, the jets from black holes, the corona of the sun, plasma. We were taught the exception and told it was the rule. How does plasma form? The short answer is, give matter enough energy. The mechanism is ionization, stripping electrons from their atoms. You can do this with heat, with intense radiation, with strong electromagnetic fields, or with high-energy particle collisions. In the Sun's core, temperatures exceed 15 million degrees Celsius. At those temperatures, matter isn't just ionized, it's completely ionized. Every electron is free. The plasma is a dense sea of bare nuclei and unbound electrons, and it's in that environment that nuclear fusion occurs. The same plasma that is the Sun is also the fusion reactor that has powered it for 4.6 billion years. Lightning is a different route to the same destination. A bolt of lightning ionizes the air along its path almost instantaneously. Temperatures in the lightning channel reach roughly 30,000 Kelvin, 5 times hotter than the surface of the Sun. For a fraction of a second, a channel of plasma connects cloud to ground, conducting electricity with almost no resistance. The thunder is the shock wave from air explosively expanding as it's superheated to plasma. The ionosphere forms differently, not from heat but from radiation. Solar UV and X-rays have enough energy to ionize atoms in the upper atmosphere without raising the temperature dramatically. The ionosphere is a weakly ionized plasma. Not every atom is ionized, just enough to make the medium electrically conducting, enough to reflect radio waves, enough to interact with Earth's magnetic field and produce the aurora. Partial ionization matters. You don't need every atom stripped to get plasma behavior. Even a small fraction of free charges, a few percent, is enough to make a gas electromagnetically active. The behavior changes fundamentally at the threshold, not gradually. The behavior. That's where plasma becomes genuinely fascinating. In a neutral gas, particles interact through collisions, direct, short-range, local. Two atoms meet, exchange momentum, go their separate ways. The interaction is bilateral and brief. In plasma, every free charge creates an electric field. Moving charges create magnetic fields. Those fields propagate through the plasma at the speed of light, influencing every other charged particle simultaneously. The interaction isn't bilateral, it's collective. Plasma supports modes of behavior that gas simply cannot. Plasma waves, oscillations propagating through the bulk of the material without direct particle contact. Plasma instabilities, configurations that are electromagnetically unstable and release energy catastrophically. Plasma self-organization, the spontaneous formation of structures like current sheets, magnetic flux tubes, and plasma filaments. A plasma isn't a bag of independent particles. It's a medium with a collective electromagnetic identity. It responds to disturbances as a whole. It has memory, in the form of fields, that extends across its entire volume. This is why plasma is a fourth state, and not just a hot gas. The collective electromagnetic coupling is a phase change in the physics of the material, not just a quantitative shift in temperature. The relationship between plasma and magnetic fields is where the universe gets spectacular. Charged particles moving through a magnetic field don't travel in straight lines, they spiral along field lines. Plasma is therefore guided, confined, and shaped by magnetic fields, and conversely, moving plasma generates magnetic fields. The two-way coupling between plasma dynamics and electromagnetic fields produces complexity that neither alone can generate. Solar flares. Magnetic energy stored in twisted, stressed plasma structures in the Sun's atmosphere releases explosively. Billions of tons of plasma ejected into space at millions of kilometers per hour. These coronal mass ejections reach Earth in 1 to 3 days, interacting with our magnetic field, potentially disrupting satellites, power grids, and communications. The Sun's corona, its outer atmosphere, is a plasma heated to over 1 million degrees Celsius. The surface beneath it is around 5,500 degrees. Heat flows from hot to cold. The corona shouldn't be hotter than the surface, and yet it is, by a factor of nearly 200. This is the coronal heating problem. It's been known for decades. It's studied intensively. There are leading hypotheses: magnetohydrodynamic wave heating, nanoflare reconnection events, but no settled consensus. The most energetic, most observed plasma in our solar system has a temperature structure we cannot fully explain. That's not a small gap. That's the fourth state of matter in our own backyard, running on physics we haven't completely worked out. Plasma physics isn't just about stars and space. It's the center of one of the most important technological projects in human history. Nuclear fusion, the process that powers the sun, requires plasma. To fuse hydrogen isotopes into helium and release energy, you need temperatures of 100 to 150 million degrees Celsius. At those temperatures, matter is entirely plasma. There is no other option. The challenge of controlled fusion on Earth is the challenge of controlling plasma. No material can contain plasma at fusion temperatures. Any physical container would instantly vaporize. The solution is magnetic confinement. Use powerful magnetic fields to hold the plasma in a shape, typically a torus, away from any physical wall. Tokamaks, stellarators, and inertial confinement devices are all at their core plasma confinement experiments. ITER, the International Thermonuclear Experimental Reactor being built in France, is the largest and most ambitious plasma physics experiment ever constructed. Its goal is to produce 10 times more energy than it consumes from fusion. The obstacle isn't just temperature, it's plasma instabilities, the plasma's tendency to develop electromagnetic fluctuations that cause it to escape confinement before sustaining fusion. Understanding and controlling those instabilities is an active, unsolved frontier in plasma physics. The fourth state of matter is the key to fusion energy. Whether we get fusion, and when, depends substantially on how well we understand plasma. Zoom out to cosmic scales, and plasma physics is writing the structure of the universe. Astrophysical jets, narrow relativistic beams of plasma launched from the environments of black holes and neutron stars, extend for thousands of light years, carrying enormous energy and shaping the galaxies around them. The collimation mechanism, how a plasma beam stays narrow over such distances, involves electromagnetic pinching forces and is an active research area. Pulsars emit their radiation through plasma physics in extreme conditions. Relativistic plasma in intense magnetic fields, generating coherent radio pulses detectable across the galaxy. The emission mechanism is understood qualitatively, but not completely in detail. The cosmic web, the large-scale filamentary structure of matter in the universe, may be shaped partly by electromagnetic effects in the intergalactic plasma. Cosmic magnetic fields exist at scales we don't fully understand the origin of. The universe organizes itself through plasma. At every scale, from lightning bolts to galaxy clusters, the physics of free charges in electromagnetic fields is doing the heavy lifting. Here's where honesty requires pausing. Plasma physics is not finished. It has open problems at every scale, from the corona of the Sun to the dynamics of fusion plasmas to the jets from black holes. Plasma turbulence, the chaotic multi-scale electromagnetic fluctuations in magnetized plasma, is one of the hardest problems in physics. We don't have a complete theory of it. Ball lightning, reported for centuries, physically plausible as a plasma phenomenon, has never been adequately reproduced or explained. Fast radio bursts from extragalactic sources, millisecond pulses of radio emission more energetic than anything we can easily explain, almost certainly involve extreme plasma physics we haven't fully decoded. The fourth state of matter is the dominant state of the universe, and one of the most actively researched, most incompletely understood areas of physics. So, 3 states of matter, that's what school gave you. The universe gave you 4, and made 99% of itself out of the one you weren't taught. Plasma isn't a curiosity at the edge of the periodic table. It's the state of every star, every stellar wind, every aurora, every lightning bolt, every neon sign, every fusion experiment, every astrophysical jet, every pulsar beam. It's the physics of the ionosphere above your head and the solar wind washing past Earth right now. The 3-state model isn't wrong. It's just the physics of the narrow, cool, low-energy corner of the universe where the temperatures are gentle enough for electrons to stay home. Almost everywhere else, plasma, doing everything, powering everything, structuring everything. When I look at a star, any star in the night sky, I see plasma. I see nuclear fusion happening in a magnetized plasma core. I see a plasma atmosphere with a temperature profile we're still explaining. I see a plasma wind blowing outward in all directions. The universe is 99% plasma. We learned about the 1%. That's not where the physics ends, that's where it starts.